Hello, welcome to Stars, Cells, and God, the show where we discuss new discoveries taking place at the frontiers of science that have theological and philosophical implications, as well as new discoveries that point to the reality of God's existence. My name is Jeff Zweerink. I'll be your guide today. But before we get into the discussion, I want to encourage you to subscribe to our channel, Reasons to Believe. Click on the bell icon so you can be informed of new videos. Learn more at reasons.org and by following us on social media at RTB_official. Hugh, I know you've got a discovery on from the James Webb Space Telescope, so why don't you go ahead and get us started today?
Yeah, happy to do that, Jeff. And it just got published in the latest edition of Astrophysical Journal Letters a few days ago. And it's basically addressing a common objection that people hear about the Big Bang model, how the early observations of early galaxies by the James Webb Space Telescope is posing an issue, at least for some Big Bang creation models. And so this team of astronomers said, hey, we already have had great success with a computer simulation program. It's called FIRE. That's an acronym. It stands for Feedback in Realistic Environments.
Okay.
And what they're doing is that they're looking at literally millions of galaxies and seeing if they can accurately simulate what's happening with the history of those galaxies in terms of star formation and the chemical abundances. And they've had great success for the past 12 billion years of cosmic history.
So in other words, their simulations of what galaxies should look like and behave over the last 12 billion years matches what we can see with our
Matches
telescopes.
what we can see. And, you know, that's the place where we've had good data. And where we haven't had good data is for the first 2 billion years of cosmic history.
That's part of why James Webb went up, was
That's
to
right.
get us that data.
So James Webb is now beginning to produce that data.
Right.
But one of the things that was the core of this thing that you see on the web, hey, James Webb is causing problems for the Big Bang model, is that the earliest galaxies in the universe were too bright at ultraviolet wavelengths. And so this team said, well, we've had good success with a computer simulation. Let's try it on these early galaxies. And they waited until they had a decent database. They now have good data on 25,000 galaxies where we're looking back 13.1 to 13.5 billion years ago.
So this is data that we've never had until today. I mean, we just didn't have telescopes that allowed us to see this.
Right, and they had to wait for a few months because it took a while for the data to accumulate. But they said we now have a decent database thanks to the James Webb Space Telescope. And so these would be galaxies within, say, the first 700 million years of the after the birth of the universe. So they're able to explore this region where we're, quote, seeing a problem. Some of these early galaxies seem to be way brighter at ultraviolet wavelengths than what our standard Big Bang creation models would predict.
So by way brighter, I mean, what is the problem with that? I mean, to me, on a first pass, you could say, okay, things are just brighter. It seems like there's got to be something more than just brighter there.
Well, I mean, they address that in the paper saying there's always been ways to deal with this and save the Big Bang models. You can just say, well, star formation was more aggressive in that early epoch. Or maybe what we're seeing is the firstborn stars are much more massive and numerous than what we thought. That would solve the problem. And that we really don't have to say, well, let's go and look at a distinctly different Big Bang model. They're saying that's one way to go, but other ways to go is just to look at, hey, maybe we need to understand what the first stars really like. If they're massive and numerous, that would solve the problem, or if the star formation rate. But they said, let's first, before we go down those paths, let's use our computer simulation on this study. And so what they did is they looked at...
Just a quick question before. So in my understanding of what's kind of come out with the James Webb that is a problem, a lot of times what it's argued is that the galaxies are larger and more complex or more developed than what we thought. Is this getting at that, or is that a separate problem that is being dealt with?
They're actually, in their opening introduction, are saying a bigger issue for the Big Bang models is the ultraviolet brightness. We can easily handle these other issues that are being raised. After all, the brightest galaxies are the ones you're going to see first.
Right.
And we're going to need deep imaging by the James Webb to actually get the true statistical nature of these early galaxies.
Okay.
And they're basically saying, so far, it seems to be demonstrating that, the Big Bang models are right.
Okay.
The faint, small galaxies are way more numerous than the big, bright ones.
Mm-hmm.
And they said, we'll have better understanding. But their whole point is the biggest challenge for these Big Bang models is the ultraviolet brightness of these early galaxies.
Okay, and presumably to have a overly bright galaxy, you've got to it's going to be a larger galaxy. That's going to be part of what plays into that.
Well, they're actually saying we're seeing this in all the early galaxies.
Gotcha,
They all
okay.
seem to be extra bright at ultraviolet wavelengths.
Okay.
And so they use their FIRE simulation, what's it called again? Yeah, feedback in realistic environments, and said, we've had great success for the first 12 billion years. Let's see what's going on. And they tested two models, one in which star formation happens at a continuously constant rate, and one in which it's bursty, which means you get short episodes where the star formation rate is very aggressive, then you get periods where it's quiet. So those are the two models they looked at, and they said, in both cases, you get the same number of stars forming. We're not playing with the star formation quantity. We're only playing with the way the stars form.
Okay.
Do they form in a continuous constant manner, or do they form in bursts? And what they were rather surprised to discover is that the bursty model gives you an ultraviolet excess that's 10 times greater than the steady model.
Okay.
And their whole point is this challenge to Big Bang models was based on the assumption that the star formation rate during the first billion years of the existence of the universe was constant. And
Which that's kind of similar to the conclusion we draw from later galaxies, presumably.
Actually, they're pointing out that's not the way it goes.
Okay, all right.
So when they looked at the 12 billion years where they get this really good fit, what they said is, our observations don't fit a continuous model. Star formation tends to be bursty. And so if we assume that the same situation is operating in the early universe, it takes care of the problem, mainly because they notice it has a dramatic impact on the ultraviolet brightness, whether star formation happens in short bursts or whether it's continuous. They're rather surprised, a factor of 10 difference in the two.
So is that just because when you've got a burst, you're just going to get a lot more star formation, which is going to drive up the luminosity of everything, or you tend to get more ultraviolet light when stars are forming?
Well, when you have these bursts, we see this later on in the universe. We look at what are called starburst galaxies, where star formation is happening very aggressively. You get these big stars forming as well as lots of small stars, but those big stars basically shower everything with ultraviolet radiation. The really big stars are very bright at ultraviolet wavelengths, but it also affects the behavior of the small mass stars. And so they said, hey, this is the way things seem to be in the latter 12 billion. If we assume it's the same for the first billion, it solves the problem. We don't have to appeal to hyper-aggressive star formation. We can leave the star formation rates the way they are, and we don't need to appeal. It says this fits all of our standard Big Bang models, and we don't have to appeal to saying, hey, the first stars are very big and very numerous. None of that is necessary.
So is the idea then when these galaxies are forming, when they start to coalesce, they just form a lot of stars very rapidly and then settle down to a more quiescent state?
Yes,
and that's what we see kind of later in the universe. That seems to me the way it would. I would kind of half expect that in a lot of ways.
Yeah, and you'd expect that you would get a more bursty star formation rate in the early universe, because that's when the merging of galaxies is more. The universe hasn't expanded, so you expect that there would be a higher merging event of galaxies. And what we observe in the latter 12 billion years, where you get the really aggressive starbursts, is when galaxies merge. And so you'd expect the merger rate to be even higher in the early universe. So that really fits what their computer simulation is demonstrating is going on.
So in any given galaxy, you're going to get roughly the same number of stars formed, but instead of spreading it over a long period of time, it all happens kind of initially and then settles down into a more quiescent state.
Yeah.
And that mirrors what we see going on in the universe today. We just don't see as many collisions, so there's not as many bursting galaxies.
Well, I'll give you an example. Our galaxy is in a quiescent state.
Right.
Yes, it's forming stars, but it's not forming stars at a rate that's anywhere like what we see in galaxies where they've had a recent merging event.
Mm-hmm.
And so they're saying, hey, this is the way it looks throughout the whole history of the
Mm-hmm.
universe, and we would predict that the merging rate would gradually dissipate as the universe expands, which implies you're going to get a higher merging rate in the first billion years than, say, 5 billion years later.
Right.
So,
These sorts of discoveries, I guess, when I even heard about the problems that showed up, it's like there's a part of me that didn't think that was that big of a deal. There's been enough times in my scientific career, I think when the Hipparcos, I may be drawing the name wrong, but we start getting these high resolution images of stars or data from stars, and we find out that there are stars that are older than the universe. It's like, okay, we know that can't be the case, and nobody looked at that and said, oh, our model of the universe is wrong. It just says, okay, there's more detail, or our data gives us more detail than our kind of simple models out of the lack of data allowed us to do. It strikes me this is kind of in that class of we're getting to see something where we kind of assumed, okay, it's going to play out this way, a simple model, and it just turns out to be a little bit more complex model. None of this seems that surprising
I remember
to
when
me.
they found that star, they came in at 14 billion years, and they said, hey, this is older than the universe at 13.8 billion. And on the web, people are saying, we got a problem.
Mm-hmm.
But if you actually looked at the research, it was 14.1 billion years, plus or minus 1 billion. The error bar was quite huge.
Right, but it's, there's a history of that.
Right.
These sorts of things are not uncommon, if
They're
you're
not
in
uncommon.
the field, it just happens pretty regularly.
But the tone of what you see in the peer-reviewed literature is quite different from the tone that you see.
No, and I think that's
in the
why
web
none of
articles.
these sorts of things bother me. Honestly, one that's a little bit more problematic is you go out and you say, all right, given the size of the cosmic microwave background fluctuations, there's a certain maximum size of structure that we see, and we see structures that are larger than that. And so, to my knowledge, that's still an unsolved problem. We've got ideas about that, but
It's unsolved.
This is what scientists love. It's like, how do we solve these problems? So,
Well, there's a difference between unsolved and unsolvable.
fair point. Yes.
Because, in terms of the example you just gave, there's lots of papers publishing saying this is how
Right. Yeah.
this is how it could be solved. That's quite different from people saying, we've looked at all possibilities. There is no possible solution.
Right.
Now you really do have a problem, and you begin to question the model. But if you got 4 or 5 viable solutions to the problem, it's like, let's research them and see which one solves the problem.
Well, and that strikes me, maybe that's a kind of a good guide. And I think what I've intuitively learned to do is like when I see these problems, especially when they're from a new instrument going up, I've just learned that a whole lot of discovery happens simply because you're seeing things that you weren't able to before. So when a new instrument goes up and it says, oh, we're rewriting everything, it's like maybe take a step back and say, all right, what is it that's going on here? What are we finding that's new? And do the astronomers and do the scientists think, oh, this is a radical rewrite or what? And I know at least some of this has played into, there were places where astronomers were saying when the James Webb came up, oh, we have to rethink our galaxy evolution, but people, whether intentionally or not, misconstrued that as, oh, we got to rethink everything about the universe.
Yeah, it's more like we have to adjust our galaxy formation models. If
Right.
we knew all along what had to happen, even
Exactly,
before
yeah.
James Webb went up. And also, I think we need to tell people, astronomers like you and I, we get excited about these problems. Hey, we're going to learn something. And
Yeah,
so,
just case in
if you don't
point.
have any problems, you don't have a job, right?
I know. I think there's part of that's scientists are viewed as we always, everything's always logical, rational, kind of wrapped everything up. And, I'm working in dark matter. Honestly, the idea that dark matter was fairly prevalent is kind of in my scientific tenure, kind of 30, 40 years. But this has been around for 80 years that the idea of dark matter is out there. We've been working on it for almost 80 years now and still don't have a solution to it, as in we know what kind of particle it is, that sort of thing. But that has been what is driving a lot of, hey, how can we get an understanding on this? It's a hard problem, but the hard problems
And
people get really excited about as
And we
scientists.
knew all along it was going to be hard. I mean, trying to find dark matter particles is not easy.
Exactly. Well, and I mean, dark energy plays in that same way. I mean, for as hard as dark matter might be, at least we think that might be a particle, and we got ideas. Dark energy, that's a whole different ball of wax, but it's still a fun problem to work on.
Right. So I don't think we're going to be unemployed anytime soon.
I don't think we are not going to run out of interesting problems to solve, even if you just stick with astronomy.
Okay, thanks, Jeff.
Very good. So I'm going to shift a little bit of gears here, talk about artificial intelligence, and more specifically, deep neural networks. And it was just an...
Why don't you define for us what you mean by a deep neural network?
Well, I'll get to that in just a second.
People think of a brain, okay?
Well, but that's kind of what you're getting at there, is there are... these neural networks are saying, well, hey, the way the brain works is there's this connectivity and neurons are firing back and forth, and there's stronger connections here, weaker connections other places. And so they're saying, all right, that's the way the brain processes. Can we build that sort of system into a computer? And it's modeled after that. It's not the way they do it in computers is not the way our brains do it, but it's at least modeled after that.
I think most people are used to computers calculating in a linear fashion. These neural networks do it in a parallel fashion where you have...
Yes and no. I mean, it's parallel, and it's more that the data comes in and it's run through this matrix of how are these things connected. I mean, it's doing lots of things, and it's really saying, rather than here's this path that you take, it's like there are lots of different things at play, and there's lots of different things that can influence. In a way, it's of accounting for that. And the deep just means that there's a lot of it. I mean, you can have a neural network that's 2 or 3 nodes and only 1 or 2 deep, and that's just a small neural network. Whereas these are 8, 9, 10, 12 networks, thousands of nodes in each layer. Right. And so, as you can see, part of the challenge in that is that the more nodes you have and the more layers you have, the connections you have grow exponentially, I'm drawing a blank. They grow geometrically instead of arithmetically. And so one of the challenges you run into is, as we've gotten more of these deep neural networks running, we've got enough data to train them, they've gotten very good at saying, oh, that's an image of a dog, that's an image of a cat, that string of sounds is saying this, and so I'm using that language kind of sloppily, and I'll get to that in a few minutes. But they're getting very good. These neural networks are getting very good at categorizing and processing input and giving an output that would say, okay, yeah, we agree with that. One of the things they're finding though, is that there are these idiosyncratic or what I call invariant behaviors. And so just to kind of give an idea of the task. So when we go out and say, all right, dogs, I can look at pictures and say, okay, that's a dog. And if the dog's from the side, from the front, from the back, from the top, dark lighting, heavy or high lighting, low lighting, weird colored lighting, all of those sorts of things, I can still look at that if I'm functioning properly and see dog. And virtually all humans will look at that and see dog. And so what this particular set of researchers were looking at is that very often, in order to do that kind of invariance, so regardless of the conditions, if it's a dog, we see dog, that's an invariance in there. And what these scientists are noting, or these researchers are noting, is that there are other types of invariances that show up in these models that are that don't match the way humans do. And particularly, they looked at both auditory and visual representations. And what they were able to do is say, all right, we're going to query, what's going on here, and show what's going on, but that at various stages in the neural network, they're able to come up and say, okay, give me what they use the term a metamer of what you're talking about there. And so, I don't know, I was trying to look for a good example of a metamer, but one of the ways you can do that is, say you've got a ball that's a white ball. You can shine a yellow light on it and it will look yellow. Or you can shine certain kinds of red, green, and blue light on it, which are not yellow, and your eyes will perceive it as the same way. So even though there's different conditions, you get the same response. And so in the context of this AI, or of this neural network, what they're looking for is, given that you gave this response of cat or dog or whatever, what other situations, you're kind of querying the network to say, give me another instance where you draw the same conclusion or where you get to the same activation of dog. And what they find is that it will produce stuff that is incomprehensible to humans. One of the examples is, got a picture of a dog, and as they track through various places, they'll show other pictures of a dog, and then at some point, it'll just become this kind of random selection of blue, green, and red pixels on it. But the network will say, this is the same thing, whereas no human would look at that and say, they'd look at this other image and say, what in the world is this? Whereas everything else here falls in the dog category. And so there's something about these neural networks that are the way they categorize and process is very different, or something's distinct from the way humans do that.
So they figure out what the problem was?
Well, that's part of the question. Is that a problem? Is there really a distinction there, or do we just not have that sufficient level of detail to figure out whether humans do that or not? And they're inclined to think it's actually a difference in the way the neural nets do, because one of the things that is true of all of these neural nets is that they are trained to do things to mimic human behavior. So they're trained to say, okay, well, we've got all these images. Humans can process that and say, that's dog, that's cat, that's snow, whatever. And so they're training these neural networks to do the same thing. But in a very real sense, they're mimicking human behavior, not copying human behavior. Because the one thing that is true about you and I, when I look at that, I'm looking at dog. I'm not saying, okay, I'm not looking at it pixel by pixel, breaking it down, finding correlations. I am doing some level of that, but I'm looking at that and correlating that with there are ideas that flow in my head. So I have an idea of what a dog is, and I'm asking, does that match dog? Does that match cat? Does that match? The neural network doesn't have these ideas of dog, cat. It just has string of input, string of output.
Right.
And so, I think that's an important distinction to remember. And kind of my takeaway with all of this is not that, wow, AI is bad or neural networks. It's like they do some fascinating, really cool things, but they're just highlighting there are these differences between humans and machines. And the better the human machines get at mimicking our behavior, we're inclined to attribute human-type thought and emotions to them. But I think it's important to remember that they just are doing things differently. They're doing things similarly, but they're fundamentally operating differently, because when you and I are processing sounds and visual cues, we're thinking in terms of thoughts and ideas, not input or string of data in, string of data out. Whereas all of these neural networks are thinking string of data in, string of data out. Or they're not even thinking. It's like, given this thing, this correlates with this output. I'm thinking, ooh, that looks like a dog. Well, it kind of looks like a dog, but maybe it could be a cat. How could I distinguish those? There's just an entirely different process going on in my mind than there is in this neural network.
Yeah, and I would expect that where you're going to get neural networks doing better, it's as if you cut off all the tangents. We humans can say dog, cat, airplane, whatever. I would imagine that this neural network would do a lot better if all I had to do is identify the dog breed. In other words, knows in advance, I'm only looking at dog images. I don't have to worry about things that are not dogs, only dog images. Now you've narrowed the scope of speculation and tangent movement of the AI, and my guess is it'll do a lot better saying, this is a German Shepherd,
right?
This is a Chihuahua, than if it's asked to say, tell me whether or not this is a dog or something else.
No, and that's true. And I think these things are actually very good at mimicking the human response. What we would say is dog is what they say is dog. What this particular group was looking at is now asking what else falls into that categorization. And there's lots of other things that are clearly not in that categorization as far as humans would say that these machines would, or these networks would do. One of the interesting things that flowed out of that, though, as they were looking, because different networks have these different invariant idiosyncrasies, if you will. And one of the things that they found is, there were processes to put in place which could minimize some of that. I mean, especially in the middle stages, tends toward the later stages, the deeper into the process, it became harder to do. But one of the things that I found very interesting was that these metamers that were invariances that were unrecognizable by humans, is that very often by looking at other models, they could predict, or if the other model didn't recognize it, chances are the humans wouldn't recognize it either. And I mean, maybe I'm drawing too much of an inference here, but I just think of how humans operate, that humans don't operate in a vacuum. They operate in a community. We're designed to operate in community. That I wonder how much of these things we may actually do, but there's just enough interaction of me with my parents, me with my brothers, me with other people in the community. So where I would develop these things and say, oh, yes, this is all the same class, somebody eventually just in that community of interaction, I would have put that in the same category, but it's wrong. And so that community aspect of training also comes into play here, because every one of these are just being trained by it's kind of operating in isolation, if you will, as opposed to interacting with.
Well, they use your analogy, Jeff. I mean, if you're in a community of humans, we all have different databases and different experiences, which means we're going to have a broader perspective than, say, what a machine would do. That, after all, AI is limited by the databases that you give it.
Well, at least current versions of AI are. Yeah, absolutely. And so, I think I could see a couple of places where I think this social aspect is very interesting. I could also see where people would look at that and say, well, see, what's going on there is that it takes the community to define what's right and wrong. It's not the actual data itself. And I think that's a misread of this. But what is true is that, if this is truly a dog, you and I will agree. If we get out here and we disagree, some aspect of the community is going to help us decide which of us is in error about this. It's not that dog becomes an undefined concept enough. It's that each of us had these idiosyncrasies, but in the context of community, we can refine them and draw them in or figure out how to deal with them. So we say, okay, in my way of looking, I'm not looking at it the way the community does, therefore I'm likely wrong and I need to adjust the way I evaluate, redefine my categories to make sure that they're properly drawn and accurately reflect reality. And so I thought that kind of communal aspect of this was interesting, because in terms of the training, whether the neural net or the deep neural network was trained supervised or unsupervised, they developed these idiosyncrasies. So it isn't just a matter of being supervised. It's almost like there needs to be some level of interaction with a group of AIs, if you will, or a group of neural nets. And again, that's so critical to the way humans develop. Well, it wouldn't surprise me if we're going to get human-like behavior, we need to model that aspect of it as well.
Okay, sounds good.
So I just think this is kind of, I see in these two discoveries that as we continue to grow, one, we see that what God has revealed in Scripture about this universe, that we live in a Big Bang type universe and that we are people created in His image, that the more we study, we actually find evidence to support that the evidence for that grows stronger. So,
and we can produce new databases.
Exactly. Well, thanks, Hugh. I appreciate your comments today. And I want to thank you for joining us and encourage you to join our Star Cells and God discussion in the comments below. Remember to like this video so you get new content. Subscribe for more content. We have new episodes released each Wednesday of Star Cells and God. They're available here on YouTube and on your favorite podcast app. Be sure to share this video with a friend. And remember, the more we know about science, the more reasons we have to believe.